In this video, we're going to prove the main result of the Frisch-Lovell theorem, that is that beta 1 can be obtained by a different way than the usual OLS, that is x1 transposed times m2 times x1 all inverse times x1 transpose times m2y. So we got that by recalling the OLS generating parameter equation, that is x transposed x times beta, that is equal to x transposed y. So we recall that x is composed by x1 and x2. Then we have that the transposed one will be x1 transposed and x2 transposed times x1 and x2 times beta 1 hat times beta 2 hat. That will be equal to x1 transposed x2 transposed times y. So we proceed on the multiplication of the matrices. That will be x1 transposed x1, x1 transposed x2, x2 transposed x1, x2 transposed x2 times beta 1 hat and beta 2 hat. That will be equal to x1 transpose y, x2 transpose y. Now, to derive beta 1, first of all we have to define beta 2 actually. So we simply take the second line of this of the resulting equations, because if we develop, we continue to have x1 transposed x1 beta 1 plus x1 transposed x2 beta 2, that is equal to x1 transposed y, and then x2 transposed x1 beta 1 hat plus x2 transposed x2 beta 2 hat and x2 transposed y. We take the second line equation of this matrix system, and then we have that beta 2 will be equal to x2 transposed x2 beta 2 times x2 transposed y minus x2 transposed x1 beta 1. Then we pre-multiply by this inverse on the other side, on both sides, and then we are left with x2 transpose x2 inverse times x2 transpose y minus x2 transpose x2 inverse times x2 transpose x1 beta 1. So we take the first equation of this system, that is this one, and we put this beta 2 in here. Then, therefore, we have that it is equal to, we rewrite it again, the first line, so x1 transpose x2 beta 2, that is equal to x1 transpose y, and we substitute the beta. So we have that this is equal to x1 transpose x1 beta 1 hat plus x1 transpose x2 times x2 transpose x2 inverse times x2 transpose y minus x2 transpose x2 inverse times x2 transpose x1 beta 1 hat, that will be equal to x1 transpose y. So what we notice here, if we multiply this by this, we have this x2 times x2 transpose x2 inverse times x2, that actually will be equal to h2, because it is the x times x transpose x inverse x transpose for the matrix of the coefficient we are putting, the regressor we are putting in this x2, and that is our projection matrix for the regressors in the second x matrix. So we are left with x here. So this time, this stuff here, it will be equal to x1 transpose x1 beta 1 plus x1 h2 y. And even here we have that this x2 multiplies this x2 transposed x2 inverse times x2 transposed, that will be also equal to h. So we have x1 transpose h2 x1 beta 1 hat, that is equal to x transpose y. Now we move this on the right hand side, and we are left with x1 transpose x1 times beta 1 hat minus x1 transpose h2 times x1 times beta 1 hat, that is equal to x1 transpose y minus x1 transpose h2 y. And then what we notice here, like we are multiplying some stuff, we are multiplying this one, there is a identity, we can imagine an identity matrix here, and the same for this one. So what we are doing, we factorize this stuff, and then we have that x1 transposed is multiplying the identity matrix here and the projection matrix here. And then this is equal for both. So we put it on the right hand side, on the right. On the right hand side it happens the same. So we have x1 transpose the identity matrix of n size minus the projection matrix of the second matrix of x times y, and this is equal to the residual maker matrix, that is m2. Then we are left with x1 transpose m2 x1 beta 1. Then we have x1 transpose the residual maker matrix 2 times y. Then we pre-multiply by this inverse, so we are left with beta 1, that is equal to x1 transpose m2 times x all inverse times x1 transpose times m2 times y. And so in this way we have proven that the final result of the Frisch-Lovell theorem